Well, good afternoon, ladies and gentlemen. Welcome to the Royal Society Library. My name is Keith Moore. I'm the head of the library here, and we're delighted to see so many people for this afternoon's event. Now, you will see that this is one of a series of lectures that we do here. So if you'd like to come to any of the other ones, if you're a first-timer here, by all means do so. And I'm very grateful to Rupert Baker and Felicity Henderson for making this programme possible. A couple of small announcements. We do have a new China exhibition downstairs in our exhibition area. If anybody would like to see that today, you would be very welcome. It has just opened. During the talks, if you could switch off your mobile phones, please, that would be very good. Don't turn them on silent, turn them off completely. Our AV team get very upset if we don't do that. And the most important thing at all, I'd like to introduce you to Selena Fox, who is going to give our talk for this afternoon. She is what's described on the web as an art and cultural historian, trained at Cambridge, Harvard and Oxford, and has formerly worked as keeper of art at the Museum of London. The title of the talk today is Surveying the Scene, Engineering the Machine, the Drawings of John Smeaton. It's one I'm looking forward to. I used to be the librarian at the Institution of Mechanical Engineers, and we rather look down on these terrible civil engineer fellows, so I'll look forward to learning something this afternoon. So if I can hand over to Selena.
Thank you very much. Firstly, I think I ought to say that this talk is dedicated to A.W. Smeaton, without whom none of us could work on Smeaton. He is the great master of pulling together Smeaton's achievement and interpreting the drawings. Just to explain what I'm going to do, it's not going to be wholly a picture show. We've got some of the drawings out, and my rather shaky slides have been taken to illustrate the second half. But the first half, in the first half of my talk, I want to explain what was the purpose and the nature of engineering and surveying drawing, because it's quite hard. We take it so much for granted, but then they didn't. It was much more of a sort of a process that was developing. So firstly, how did they get here? There are 1,200 drawings, and they survive in the archive here. They were on 995 folios, first bound into 6 massive volumes, and now split into 11 parts. And we've got 3 of the parts out. Most of Smeaton's manuscripts relating to his practice, plans, drawings, 48 folio volumes of reports and estimates, letters and bundles of other papers were acquired in batches in 1793, 1794. That's just after Smeaton's death in 1792. And they were bought by the then president of the Royal Society, Sir Joseph Banks, who paid £150 to Smeaton's heirs, his 2 daughters and sons-in-law. When the Society of Civil Engineers published a selection of Smeaton's reports and estimates in 3 volumes in 1812, the illustrations were prepared from Smeaton's original drawings by the engineering draftsman and technical writer John Ferry, Jr., who lived from 1791 to 1851. Ferry also used the drawings as the basis for engravings to other publications, notably Abraham Rees's Cyclopedia. Following Banks's death in 1820, Ferry retained the drawings and associated letter books, etc., under the terms of the second codicil of Banks' will. And in 1821, he organized the drawings into the 6 volumes. He continued to use and annotate them well into the 1840s. After Ferry's own death in 1851, his son, Edward Ferry, disposed of the bulk of the Smeaton papers, but when he died in turn in 1913, he willed the 6 volumes of drawings to the Royal Society. So in a roundabout way, they came back to the Royal Society. He also willed his father's annotated copy of Smeaton's great work on the Eddystone Lighthouse, which is one of these volumes here. As a result of Edward Fairey's dispersals, Smeaton manuscripts are now held not only by the Royal Society, but also by the Sutro Library in San Francisco, the Institution of Civil Engineers, Trinity House Library, and other bodies yet to be fully traced. So that gives you an overview as to why they're here. Now, the drawings themselves, what do they mean? I want to place them in a historical context and to explain their purpose. The drafting skills of surveyors and engineers developed in the 16th century through the application of geometry, using new types of surveying instrument. At their most basic, drawn surveys, together with numerical calculations, provided reference points for establishing costs. They also constituted the only means of providing a reasoned exposition of territory in its overall extent and its particular features. The introduction of signs denoting the impact of man, fortifications and settlements, roads, bridges, canals, and various kinds of machine marked the means adopted from conception to execution of attempting to control the territory. Therefore, learning to draw surveys could also extend to learning the rudiments of engineering. Engineering drawings were primarily expository, intended to convey with clarity, order, and definition an increasingly varied and complex array of technical processes and products. Following Vauban's cardinal rule that fortresses must take advantage of natural terrain, the engineer's first task was to explore the territory and survey its potential. As the British engineer said of the Japanese bridge on the River Kwai, I wouldn't start from here. Like surveyors, engineers relied not only on direct observation, but also on mathematical calculation to make drawings, either in perspective, as if viewed from somewhere, or in projection, in other words, plan, elevation, profile, and section, as if viewed from nowhere, free of human intervention. In both surveying and engineering drawing, there is always a tension between the desire for rationalization and precision, and the diversity of local or particular circumstances. 18th century surveyors and engineers realized the inability of mathematical theory fully to encompass the behavior of the material world. They had to shape both the context and content of innovations, to consider the external environment and to bring its potentially disruptive forces into their domain. In other words, they had to bridge the gap between an ideal conception of the mind and its practical execution on the ground. Drawing provided the means of achieving this, for at its most primal, it lies at the boundary between the mind and the hand, the idea and form. Many features an engineer thinks about, even today, cannot be reduced to unambiguous verbal descriptions or mathematical formulae. They are dealt with in the mind by a visual, non-verbal process. Engineers use drawings to experiment and plan, to clarify the tentative and convert their ideas into practical specifications in the world. The visual language employed for the purpose evolved slowly in Britain. Surveyors, engineers, and their draftsmen oscillated between the need to establish conventions and the need to imitate nature, between geometrical abstraction and empirical observation. The retention in drawings of idiosyncratic naturalistic features based on direct observation was not simply a response to particular circumstances, the inevitable result of undeveloped systematics, or even personal preference. Engineering is always social engineering, intended to fulfill a particular application or purpose in the real world. The successful accomplishment of the task involves a series of negotiations with different people of varying levels of skill and understanding. Designs and specifications are products of social processes. 18th century surveyors and engineers were well aware of the need to present their drawings to clients in a manner that was most likely to be comprehended, to gain approval, or to help raise the necessary funds. This usually meant retaining a degree of informal pictorial expression and even the incorporation of various forms of polite embellishment to make the case, without compromising the display of professional authority. Pictorial elements also helped workers who were not necessarily well versed in geometry to understand what was required. Artisans had long used freehand sketches as a bridge between knowledge and manual dexterity. So the difference between the design drawing of an engineer and the direct design of an artisan was on format rather than conception. Drawings served as formal instructions. They were a means of attempting to control the potentially uncontrollable across time and distance, demonstrating an enlarged conceptual span. At their most precise, drawn in projection with the help of mathematical instruments, they provided master patterns to which far-flung suppliers had to conform, enabling different tasks to be allotted to different groups. Drawings could also be used, if necessary, as a means of guaranteeing the end results in contracts, or as a way of settling disputes. Yet the limits of drawings as working tools in an age before precision engineering were understood. Surveyors and engineers did not merely sit in their offices, like gentlemen in their studies, drafting dream projects and hoping they would be executed by remote control. We find them travelling along potholed tracks in all weathers at all times of year to survey dank fedlands and highland passes, or to supervise the construction of windmills and pumping engines. They toiled away in remote inns on their drawings and reports before presenting them with a flourish of confidence to estate owners and agents, committees of proprietors and investors. Drawings made on the basis of site visits would, it was hoped, forestall expensive mistakes in the actual construction. Although they transmitted information from a chief engineer to a resident engineer and thereon down the chain of command, problems inevitably cropped up on site, which required further visits and more drawings. It took an experienced mechanic, familiar with the methods involved, to reproduce the device from a drawing alone. Direct personal contact was crucial for the productive interchange of the overt and the tacit knowledge needed to construct a novel machine. And no drawing could represent the tactile skills required to make the thing work. The hands-on experience of mechanics, millwrights, carpenters, smiths, and other skilled men was still crucial for the successful completion of the task. It is the insistence on empirical data gathering and the continual experimentation, as well as theoretical knowledge, that marks the 18th century surveyors and engineers as, I would maintain, the true heirs of Francis Bacon. By placing heavy reliance on exhaustive description and rationalization, collating the data on a project and presenting it in the form of drawings and written reports, which exuded an air of authority, yet were grounded in reality, they carved out careers which increasingly distinguished them, not only from the realm of the artisans with their dark trade secrets, but also from that of dilettante amateurs with their fantasy sunbeam schemes. Drawings empowered surveyors and engineers. They provided visual evidence of correct modes of reasoning, of systematic research, and sober experimental inquiry. They also bear testament to the increasing scale and sophistications of the works undertaken. The fact that such material was increasingly retained supported the claims made by their makers of belonging to professions apart. Now, Smeaton and drawing. John Smeaton was born at Orsthorpe Lodge in the parish of Whitkirk, 4 miles east of Leeds. He was the son of an attorney. In the way of great engineers, he was precocious mechanically, building a model steam engine with which he pumped one of his father's fish ponds dry, killing all the fish. Having abandoned a legal career to become a scientific instrument maker, he was recognized early on for his exceptional talents and nominated a Fellow of the Royal Society by Lord Charles Cavendish as, quote, a maker of philosophical instruments, a gentleman well known to the Society for his great skill in the theory and practice of mechanics. He was duly elected in 1753 at the age of 29. Drawings were crucial for Smeaton's work. As he said, the rudest draft will explain visible things better than many words. Thinking of himself as an independent artist, he says, who designed schemes for which others would contract to supply materials and carry out the construction, he worked with rule and compass, pen, ink, and paper, and figures, giving his clients the best advice with all the, quote, plainness and perspicuity he could muster. He executed the scale drawings himself, but as he became more established, he employed a draftsman, first William Jessup and then Henry Eastburn, to make 2 fair copies, usually on fine Villadari laid paper, one for the office, one for the client, while his daughters often assisted with the shading and finishing. His drawing room and study were on the 3rd floor of a purpose-built tower at Austhorpe Lodge, while in London he was based in a watchmaker's shop run by a friend in the Strand, until he acquired his own rooms at Gray's Inn in 1783. At the end of his life, he wrote, I do not think it within the compass of human knowledge to form the best possible design at once. Things are far better finished by touching and retouching, as is usual and necessary to the greatest painter. Obviously, he didn't think of himself as an artist in the polite sense of the term. Ever the bluntly empirical Yorkshireman, he regarded the plates to his most sumptuous published work, a narrative of the building and a description of the construction of the Eddystone Lighthouse with stone, as, quote, in reality, little more than geometrical lines drawn to explain geometrical and mechanical subjects. If any of them puts on the appearance of anything further, it is to render it more explanatory and descriptive. They are, in reality, not meant as pictures. Nevertheless, he insisted that, like fine prints, they should rest flat and not be folded, so that their meaning was not compromised, hence the size of the volume. The 23 plates were engraved by Edward Rooker and James Record, and printed on the highest quality paper supplied at no extra charge by his friend James Watman. This insistence on legibility is evident in the 6 volumes of drawings organized by Fairey under these headings: windmills and watermills for grinding corn, mills for various purposes and machines for raising water, fire engines for raising water, bridges and buildings, canal works, sluices and harbours, and the last one, canals and river navigations. Water and windmills constituted Smeaton's first professional incursions into what he called civil engineering. In 1753, he was commissioned to design a watermill at Halton, Lancashire, word presumably having got around of the experiment he was conducting on water and wind power using working models of mills. Smeaton had no doubt there was a rational numerical basis for his design work. Writing to a client in 1786, he said his objective was, quote, to get the most power possible out of a given quantity of water in dry seasons, and that the construction of mills as to their power is not with me a matter of opinion, it is a matter of calculation. To assess a prospective mill site, he needed to know the fall and quantity of available water, on the basis of which he could make calculations to, quote, settle the sketch for the wheel, the water trough, and the shuttle. But in the paper he delivered to the Royal Society in 1759 and published the following year, concerning the natural powers of water and wind to turn mills and other machines depending on circular motion, he also emphasized the difference between the model and the performance of a machine in large, stating that he deferred presenting his conclusions to the Royal Society until he had, quote, the opportunity of putting the deductions made in real practice in a variety of cases and for various purposes, so as to be able to assure the Society that I have found them to answer. Smeaton's caveat as to the utility of models was loaded in the context of the Royal Society. His whole course of experimentation was driven by practical problems, not hypothetical concepts, and he relied on empirical observation, not theoretical hydrodynamics, and he tested his models in the real world. Water was, of course, the main source of power in the 18th century Britain, and over the next 40 years, Smeaton was responsible for nearly 60 water mills, employed variously for grinding corn, extracting oil and gunpowder manufacture, sawing wood, working iron, and fulling woven woolens. He was also involved in planning and supervising modifications to existing mills, and occasionally was called upon to arbitrate in disputes. A typical set of drawings comprises an overall plan of the site and/or of the mill, a plan, section, and elevation of the machinery overall, details of the water wheel, and sections of other parts, especially if they were to be made of cast iron. But the volumes also include rough drawings, and a few made by others, including Fairy. Smeaton worked in partnership with men who would carry out his plans, sometimes leaving them to design the framework, so long as the proportions of the parts he designed were strictly adhered to. The design for the water corn mill executed in 1754 at Wakefield for Sir Lionel Pilkington are typical of his early work, with hatching and washes in different tones to give a sense of texture and depth. But note on the right the additional drawing of the Hurst, in other words, the large wooden frame, of the spur wheel drawn in plan and pinned on a rolled sheet to the sectional elevation. This picturesque trompe-l'oeil conceit, surely intended to captivate the gentrified owner, was not adopted on any other occasion, a sign perhaps of Smeaton's increasing confidence in the authority of his chaste drawings to command attention on their own terms without polite embellishment. More generally, his drawing style followed that employed in the Dutch mill books he had studied. This is one example, and one of the most comprehensive ones. Smeaton visited Holland in the summer of 1755, although he was not over-impressed by their machines and windmills. Smeaton's 1765 drawings for Kilnhurst Forge, this was a hammer mill near Rotherham, and they start with a general plan of the forge, and then plans and elevations for the water wheel and the machinery for the hammer, for which Fairy also made an unfinished perspective. You can see that there, and I put them together. Different drawing styles, obviously. As usual, Smeaton took into consideration the role of the craftsman on the spot, writing, quote, "The rest of the machinery, being framing or harness for the hammer, is supposed to be the subject to the corrections of the forge carpenter, and are only shown in the design to mark their relative place." So we get another page which represents the designs of the forge manager, Mr. Cockshut, for the harness, with the different parts identified by name, presumably to ensure they were both speaking the same language. The most famous and by far the largest water wheel erected by Smeaton was that for driving the pump on London Bridge, under the fifth arch in from the Surrey shore, which he made for the committee of the London Bridge Waterworks. This was huge. It was 32 feet in diameter, with 24 flat floats, which were 4'6" deep, driving forcing pumps through wooden gears. It worked for nearly 50 years, from 1768 to 1817, and then was replaced in the last decade or so of its life by an iron wheel. But before its removal, Fairy made this perspective. I'm so sorry it's difficult to see, but it was very difficult to photograph. which he later used to illustrate an article on water in Rees's Cyclopedia. There they are both together. Smeaton's interest in the waterworks continued into the 1780s, for the collection includes 2 large engravings. They're huge, and they were terrible to photograph. But they represent the receiver and distributor for the mains at the London Bridge, drawn in elevation and planned by their designer, John Foulds, the chief millwright and surveyor, and dedicated to the trustees. So it's interesting, you do get these drawings showing technical feats produced for a broader public by means of engraving. From the 1750s, Smeaton used an increasing amount of iron for the parts of both water and windmills, and once he became consulting engineer for Carron Company's ironworks in Falkirk, he was able to experiment with and develop the use of cast iron parts for machinery, one of his most important contributions to mechanical engineering. Orders for Carron came mainly through the recommendation of engineers, and the company itself disclaimed any specialized skill in design or even construction off-site, and was dependent on drawings to be able to produce the parts. Smeaton acted as their intermediary and interpreter to the outside world. Between 1769 and 1789, he designed cast iron axles for their 8 water wheels against the prevailing wisdom that they would break because they were so brittle. And this marked the end of the era of the wooden water wheel, the construction which obviously lasted for centuries. He was also responsible for the design of Carron's water-powered machinery, which was beyond the capability of the average millwright, comprising the blast furnace, blowing engines, forge hammers, rolling and slitting mills, edge tool grinders, and cylinder boring machines. This is the cylinder boring machines. They posed a particularly complex problem because of the unpredictable nature of the load. In Smeaton's words, the circumstance of the thing to be bored, that is itself a matter that cannot be reduced to any exact calculation. His mechanical improvements and innovations can be traced through the drawings in the second Royal Society volume, relating to everything from dams to shot moulds and buckets. Here he also introduced a new type of furnace tuyere or nosepipe for the blowing engine, which ensured a more complete combustion. Smeaton worked with the resident engineer George Matthews, but it seems that their collaboration was not always seamless, for Matthews sometimes did not follow Smeaton's designs, as Fairy annotated on some of the drawings. The drawings in Volume 1 track Smeaton's innovations in windmill design. The first recorded 5-sailed mill in England for a flint for china and pottery mill at Leeds of 1774, and the first known representation of a fantail or tower mill, chimney mill at Newcastle upon Tyne, the drawings for which are dated 1782. The engineering historian Tony Woolrich was able to make a 1 to 24 scale model of it from Smeaton's drawings, which is now in Newcastle Museum. In other words, Discovery. On to steam engines. In his youth, Smeaton had been interested in the Newcomen atmospheric engines installed at a colliery close to the family home in Yorkshire. A sketch of a fire engine made around 1741 appears to be the earliest drawing made by him in the Royal Society collection. In the late 1760s, perhaps prompted by the atmospheric engines he'd encountered as one of the receivers of the Greenwich Hospital's estates in Northumberland and Durham, he returned to the subject, constructing an experimental engine in his workshop, conducting systematic engine trials in the Newcastle area, and obtaining performance data on Newcomen engines in use in the north of England and Cornwall, with their average lifting power per bushel of coal. He conducted 130 tests himself, which formed the basis for the improved performance of his steam engines through the better proportioning of the working parts, thereby almost doubling the efficiency of steam engines. But the power produced was still very low due to the heat wasted through using the working cylinder also as a condenser. And by 1771, of course, Watt had confided in him his proposals for a separate condenser, which Smeaton generously acknowledged would supplant his own innovations. In 1785, Smeaton headed the proposal form for Watt's election to the Royal Society. Smeaton's drawings for atmospheric steam engines again helped to convert theory into practice. He still needed to take into consideration the topography of different sites. Thus, in a letter dated 13th of May 1777, asking Smeaton to erect a pumping engine at Great and Little Lumley Collieries, County Durham, on behalf of Lord Scarsborough, Edward Smith stated the quantity of water to be drawn in an hour and the depth to be drawn, but also requested him, quote, to take a view of the ground and to give his opinion in the manner it is to be desired to be done. The set of drawings produced for the engine with a 52-inch produced for the engine with a 52-inch cylinder at Prosperous Pit, Long Benton, Northumberland, in 1776-77, commenced with a general plan encompassing the site where the machine was intended to be erected, the wagonway from it, the engine watercourse, and the engine itself. A more detailed plan of the pit, that's the one on the right, showing the rise of the ground, was also made. There were also plans of the foundations for the water gin used to draw coal and of the old steam engine used for draining the mine. These all provided the context for the design of the new steam engine. Smeaton's most powerful engine was the massive 72-inch cylinder engine at Chasewater Mine in Cornwall, the drawings to which of 1774 to 1775 are exemplary. The first is an upright section of the engine house with an explanation, scale and measurements, and dotted lines to represent the parts hidden from view. Smeaton went out of his way to assist his client, in this instance, the Yorkshire Copper Company and its new manager, Thomas Wilson, taking considerable care over the architectural form of the engine house itself, bending over backwards to ensure that his drawings would be understood, and giving some scope for decision-making on site. That's the working gear. And here we have, this is drawing number 11 of the outside and section of the wooden injection pipe, with a plan of the injection cap and section of the lifting clack or the valve. And the instructions were even given on this with regard to the type of wood to be used, box, and if not crabtree, holly, beech, or another hard wood. Although individual drawings were made for each commission, Smeaton also attempted a certain amount of standardization by scaling up common parts, the cylinder, the boiler, regulator, and beam, so that all pieces will come together and do their respective offices without material alteration. In 1779, for example, he based the designs for the engine at Middleton on those done for Dunmore Park the previous year. Yet they still required a great deal of his professional input. J.S. Allen has tracked the process of designing a steam engine for the Walker Colliery, Northumberland, in 1782 to 83, from Smeaton's surviving journals in Trinity House Library. In all, he spent 9 days on site, including Christmas Eve for the engine trials, and around 62 hours on the designs, in addition to the time his assistant, Henry Eastburn, spent copying the drawings. So finally, we come to civil engineering. His activities on river navigations and canals, bridges and harbours extended from Ireland and Scotland to the Channel Islands. In 1760, he was appointed engineer on the Calder navigation, making all the necessary drawings for the locks, weirs, floodgates, etc., on what was the most difficult hitherto attempted, with 17 locks across its 18 miles. At the same time, Smeaton was acting as consulting engineer for canals designed by others, like John Grundy and James Brindley. In the late 1760s, he started work as head or chief engineer on the largest of all his works, the Forth and Clyde Canal, with sub-engineers or resident engineers on site and 3 surveyors for the different departments, and to each attached a foreman of the digging, carpentry, and masonry. While the sub-engineer and surveyor began detailed surveying, Smeaton staked out the eastern end of the canal line and submitted 9 typical cross-sections of canal for level and sloping ground. By the end of 1768, he had prepared drawings for swing and drawbridges, inverted siphons, etc., and for 3 typical locks, as well as for aqueducts. His letterbooks on the scheme cover 770 pages, and he submitted at least 50 plans and working drawings and attended 20 meetings. The large collection of drawings relating to it include both working and numbered presentation drawings. The numerous plans for improvements to Scottish harbours date mainly from the 1770s and are in volume 6, and they show the way in which Smeaton worked with the local surveyors, improving on their original design with scientific confidence and fluency. For example, for Ayr Harbour, Smeaton annotated the primitive survey drawn by a Mr. Gregg in red and added his own soundings and compass rows before making a fair copy, annotated with elegant script and signed with a flourish. He was well aware of the dangers of relying on the drawings of others, and in a pointed nota bene added to his report, stated that if any of the measurements he had deduced from Gregg's plans, which lacked a scale, were wrong, the expense for raising the pier and lengthening the dyke must be increased or diminished in proportion as the real measures turn out greater or less than I have supposed them. Smeaton designed bridges for Coldstream, Perth, and one at Hexham, which unfortunately collapsed during the flood of 1782. After the death of his wife in 1784, he withdrew from engineering for some years, but continued with his scientific investigations and his instrument making. That's the last drawing of Ramsgate Harbour that I'm showing. All the while, his professional standing grew. The foundation of the Society of Civil Engineers in 1774 was largely at Smeaton's instigation, for he believed the interests of a profession, then in its infancy, could be better served with friendly meetings during the parliamentary session, when they could get to know one another, to promote their mutual business concerns, quote, without jostling one another with rudeness, too common in the unworthy part of the advocates of the law, whose interest might be to push them on perhaps too far in discussing points in context. During the first 20 years of its existence, principally admitted as a social club, the Society elected around 65 members, of whom 15 were the leading practicing civil engineers of the day, and others were, quote, either amateurs or ingenious workmen and artificers connected with and employed in works of engineering. A further token of Smeaton's standing from the trial, arises from the trial that took place between Sir Martin Folkes and the trustees of Wells Harbour, who blamed Folkes's embankment for the harbour's silting up. The judgment of Lord Mansfield on the 21st of November 1782 endorsed the validity of Smeaton's opinion as science, and thus thereafter the inclusion as evidence of the opinion of all expert witnesses. And this is what he said, this is what's Mansfield's judgment. It is objected that Mr. Smeaton is going to speak not as to facts, but as to opinion. That opinion, however, is deduced from facts which are not disputed. His opinion is that, mathematically speaking, the bank may contribute to the mischief, but not sensibly. Mr. Smeaton understands the construction of harbours, the cause of their destruction, and how remedied. In matters of science, no other witness can be called. I cannot believe that where the question is whether a defect arises from a natural or an artificial cause, the opinions of men of science are not to be received. I have myself received the opinion of Mr. Smeaton respecting mills as a matter of science. The cause of the decay of the harbour is also a matter of science, and still more so, whether the removal of the bank can be beneficial. Of this, such men as Mr. Smeaton alone can judge. Therefore, we are of the opinion that his judgment, formed on facts, was very proper evidence. So, just a little afterward, Mansfield's judgment, of course, recognised Smeaton's skill and empirical knowledge, as demonstrated by his drawings in the Royal Society. Compared with written documents, however, such collections, I think, have been rather underused by historians. Surveying and engineering drawings, especially those relating to private property, remain for the most part buried in solicitors' vaults or have been consigned to county record offices, where they languish, often in an extremely battered condition, separated from associated documentation and largely forgotten. Drawn surveys of mines and their associated engineering works survive in record offices from Cornwall to Cumbria and Northumberland. The drawings of Samuel Goodrich, mechanist to Sir Samuel Bentham in the Department of Naval Works, covering the crucial period around 1800 when steam-driven machinery was introduced to the Royal Dockyards, had recently been removed to the outskirts of Swindon as part of the Science Museum's misplaced dispersal of its library and archive. Smeaton's friend, the Spalding engineer John Grundy, bound the work of a lifetime into 17 quarto volumes entitled Plans, Schemes, Reports and Estimates in Engineering, all except one now in the Brotherton Library, Leeds University, and one volume, of course, in the Institution of Civil Engineers Library. The Bolton and Watt Archive, conserved in Birmingham Public Library, now contains approximately 36,000 engine drawings in 1,382 numbered portfolios. These should give you some idea of the scale of the resources available, of which Smeaton's drawings are an outstanding example. Thank you.